Okay, we're in pre-calc. We're doing logs day one. We're assuming a little bit of pre-knowledge on logs, but not much. So I'm going to start at the very beginning, a very good place to start. If we have 5 to the x is going to equal some number like this, that was an exponential, right? And let's say that I wanted it to equal 25. Well, then that's really easy. You can say 5 to the second is 25. You might be asking, well, you haven't done anything with logs. It's because logs are very closely related to exponentials. That's why, surprisingly enough, we just finished exponentials. And now we're doing logs because they're related. All right, so this is an exponential. It's got x in the exponent, and it's an easy one. 5 squared is 25. X must equal 2. But the problem comes when it doesn't equal something nice like that. Let's say 5 to the x is equal to 27. Well, I know it's 5 to the second to be 25, so it's got to be close to 2. Maybe a little bit more than 2. Would you agree it might be like 2.1 or something? All right, how do you get the exact answer? That's where either we told you could graph both sides and see where they'd cross. And I hope you remember that an exponential like this looks kind of exponential growth. You remember these? They look like this. We cross the line. If this was y equals that, the other one's y equals 27. A straight line at 27. So you go up here to like 27 and you go, there's a straight line, and wherever they cross, that would be the answer. That's a way to solve them. But that's not the best way to solve them because there weren't graphing calculators sitting around in the old days. And there's this whole other branch of math called logarithms. Logs are very handy for quite a few things. Actually, logs are used in the decibel scale. The log scale can take something that's a huge range and simplify it down to a scale of like 1 to 10. Like, for example, the Richter scale. You heard of that one? There's a huge range in earthquakes. We just had one recently in Nepal. There's almost always one about the time I'm teaching this. It's just kind of handy. Not exactly a happy thought, but they happen. And so the huge range of earthquakes can be from so slight you can barely even feel the earthquake. There are earthquakes all the time and you don't even feel them. Okay? And those happen fairly frequently, and they're just a tiny little tremor that only a very sensitive machine could pick up. Okay? All the way up to an earthquake so violent that you would not be able to stand up. It would throw you off your feet. Okay? And obviously, if you're out in an empty field, nobody dies from an earthquake from out in an open field. Okay? It's just things falling on you is really what it boils down to. So if you're in a big city, especially in an old big city, very bad place to be because the buildings can't handle that kind of stress. We've never even had what they consider the big one. But if you have an earthquake that's anything in the 7s, 8s, 9s, those are really violent, and if you're in a city, you're going to have lots of people die. So on the log scale, a 7 on the log scale, the Richter scale 7, compared to a Richter scale of 8, it seems like just one notch up. But a log scale has a base of 10. That means that a 7 on the Richter scale compared to an 8 on the Richter scale, 10 times bigger. 10 times more violent. Okay? So that makes a really big deal when you go from a 7 to an 8 to a 9. The one in Japan that caused the tsunami that killed a whole bunch of people like a year ago, you remember that one? The Fukushima nuclear plant basically broke down and they started having almost a meltdown in that plant. That was like in the neighborhood of the 9s. And there's, again, that's 10 times bigger than this one, which is 10 times bigger than that one. So it's actually, this would be 100 times bigger than that one. Okay, so then if you get to a 10, you can imagine if it's already that violent, they say that the big one might be coming out on the west coast because there's a huge fault line. It's been a long time since they had a big earthquake there, and they think that there could be a 10 scale, which they've never had. So if you get to the 10, that's 10 times bigger than like the worst earthquake we've ever had. And those obviously, they're on a scale of 10. So anyway, the point I'm trying to get across to you is logs can be used for lots of things. Richter scale is one of them that you see every day, or decibels, how loud something is. Obviously, your ears are capable of hearing things that are super quiet. This is a weird concept, but can something make a noise, but you can't hear it? Yeah. there's things that are just too quiet for you to be able to hear. And there's also, are there things that are too loud for you to hear? It's an interesting thought. If you ever heard something that was too loud for you to be able to hear, it probably would just cause instant deafness in your case. Interesting thought. There's things that are outside your range that aren't very loud, but they're too low for you to hear. Okay, elephants, for instance, can communicate in sounds that are so low, you could be standing right next to the elephant and not hear him talking or her talking to the elephant next to you. Not a weird idea? It's outside your hearing zone. All right, so all these things have to do with logs. But I wanted just to show you that because your worksheet today is going to be just a worksheet full of equations, and I want you to know that these are actually used in your daily life, and we will get to more concrete examples on Friday. But for today and tomorrow, you're pretty much going to have problems that are related to this, 5 to the x equals 27. Because you can rewrite this using logs. Let's be specific. How could I rewrite this as a log? I would say log base 5. Now notice that's a subscript number. And of these three things, doesn't the 5 seem like a base? And the other number that's on it is the exponent of it, right? So this is a base. So when I make my log, I pick out the base and I put it down here, log base 5. And then the one thing you need to understand is that they don't go in order. It's not log base 5 of x equals 27. That'd be awesome, but it does not work that way. So therefore, what has to be next? Log base 5 of 27 equals x. Okay, all I did is rewrite this into this, which is a log statement. Why is that any better? I don't even want you to get out your calculator, but you could type that into your calculator and get the decimal answer now. Do you get that the x is alone? Do you get out in math? A lot of times we make you solve and therefore get the x alone. So rewriting logs from exponentials is a very powerful thing to be able to do, to go back and forth between logs and exponentials. So let me give you another one. 8 to the something is 60. Rewrite that as a log for me. By rewriting it as a log, you'll be getting the x alone. And I know many of you won't know how to type this in a calculator yet. That's okay. You don't need to. What you got to get good at is going back and forth between logs and exponents. Did you say log base 8 of, and it does not go in order, so therefore it can't be the x, it has to be the 60, equals x. Raise your hand if you had that one right. Okay, good. Now let me show you some patterns within this part that make you be able to do them in your head. Okay? What if I had log base 2 of 4 equals x? I want you to rewrite that one. It's a log. Make it into an exponent problem. You're going backwards now. What I mean is something to a power equals something else. Raise your hand if you think you have it. Good. Mr. W in the back row. What do you think it was? 2 to the x equals 4. Very good. Now that you see it in exponent form, can you tell me what the answer is? X must be 2. Because 2 to the second is 4. Now I can look at this thing and not even have to rewrite it in my head and say, oh, I know the answer is 2. Why? Because what I do is I rewrite this 4 as 2 squared. Would you agree 2 squared is the same thing as 4? Then, if I rewrite it that way, if the base of the log is the same as the base of this position is called the argument. This spot right here is called the argument. If the base of the log is the same as the base of the argument, then this is the answer. All right, I'm going to give you another one like that. Log base 3 of 27 equals x. That 27 could be rewritten as what to the what? The 27 is the same as what to the what? 3 to the third. If this number is the same as this number, that number is the answer. Now, I want you to understand why. I really don't want you to just believe me. I want you to understand why. Rewrite this right now as an exponent problem. Something to the something equals something. Mr. H? What's the base? I don't want to say your name on the recording, so go ahead. To the equals to the, yeah, this whole thing goes together. 3 to the x equals 3 to the third. Doesn't that make it really clear that x must be a 3? 3 to the something is 3 to the something. In case you didn't know this rule, if the bases are the same, then these have to be equal to each other. Okay, another one. Log base 5 of 25 equals x. Solve it. You can either rewrite it as an exponent problem, or you can use that pattern I just showed you 2 seconds ago, and I know the answer. Boom! How many know the answer? Raise your hand if you know the answer. Okay, good. Turn it my way and let me see if you're right. Zoom in on it nice and tight so I can see what your answer is. That's an exponential problem, but I want to know the answer. Nope. Thanks for trying. Try rewriting it as an exponential. You've got the right problem and then the wrong answer. Think about it. 5 to the 5th. I don't think you mean 5 to the 5th. Nope. You've rewritten it correctly, so what's the final answer? X equals what? Nope. Yes, 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 yes. Yes, yes, that's right. I see what you're saying now. Yes, 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 yes. For a while there, I got 8 million people said 5 was the answer. I get that you're rewriting this 25. Here. I know some of you did it this way. 5 to the x equals 25. And then you just brain farted and thought 5 to the 5th was 25. And it's not. It's 5 to the what? Second. So x must equal 2. Now, some of you others were getting your answer this way. 25 is 5 to the second. And then since these are the same, the answer is not 5. The answer is the exponent. It's the 2. That's the 2 different ways you could have got that one. All right. One more like that. It's kind of a mind bender. Yep. Yep. I don't know if you're doing it right. I'll tell you. You're close, but not right. You're right. You're right. You're right. You're right. You're right. Yep. That's the thing, except what I want is the exponent. You see, yes, you wrote the top thing right. The bottom thing's wrong. Your fraction's slightly off. Yes, yes. What I want to know is what is x? You have a nice little equation there, but what's x? Your fraction's off, but at least you know it's a fraction. Good, good, good. Your fraction's off. Good. Yes. 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 Okay. That gives me an idea of whether people are getting this. This could be 9 to the x. Another way to think of this as it goes around in a circle. You go off to the side and then you come back. 9 to the x equals 3. And then you had to think about it and go 9 to the what power would be 3? Oh yeah, that's a square root. But do you remember what fraction it is to be a square root? Square root means 1/2 power. So x equals 1/2. That's how they were getting 1/2. 9 to the 1/2 power. That means square root. Okay? It's not about taking 1/3 of 9. That's different. We wanted the square root of 9. So we used a fraction of 1/2. All right, moving on. Now there's a different kind of log. Some logs don't have a base, which is really weird. How can you not have a base? That just means it's the most common log that there is. In fact, we call it common log. And I'm going to use 100 here for log 100. I didn't say a base. So you assume the most common base of them all. And that's the base your calculator defaults to, just for example of how common it is. And it's the one that's used in decibels, and it's the one that's used in, what's it called? pH, like how acidic things are. That's a log scale. The Richter scale is a log scale. They're all use base 10. This is base 10. If I don't say what base it is, it means base 10. Okay, now it's just the same exact kind of problem. Now the thing that's weird about this one is I didn't say equals x. Well, so what? You can say equals x. If there's no other x in it, I encourage you to go equals x and then just do a rewrite. Then if I say equals x, I say 10 to the x equals 100, and doesn't it become pretty clear there? 10 to the what is 100? 10 to the second is 100. So x must equal 2. Could I have done that by making this 100 into 10 squared? Remember that way of doing it? I make this 100 into 10 squared. It's the same thing as 100. And if these two are the same, then that's your answer. All right. That's the kind where there is no base written. So again, if I did this log without a base, 10 to the third, then really what is the base? 10. Like you just, some people aren't saying it, it means I don't know if they really know it or not. Okay. That means log base 10 of 10 to the third. So then isn't that really easy to see the answer? If you caught on to this, if these two are the same, the answer is 3. So, make sense? The answer is whatever the exponent is. All right. So, would you please figure out this one? Log without a base, which means it has a base. Okay, are you doing log base 10? If it doesn't have a base, you know it's base 10. 10 times 10 is 100 of 100. And your options are, you either rewrite the 100 as 10 squared, or you say equals x and you rewrite the thing. 10 to the x equals 100. So what's x got to be? It's got to be 2. Raise your hand if you feel comfortable with what we're doing so far. Be honest. Okay. All right. Okay. Now, we have one more kind of base. Sometimes the base can be a letter. This is one of the letters that you've seen from higher algebra, but they only just briefly talked about it. Here we talk about it a lot more. Base E. Log base E. What is E? E is one of those things you should memorize, just like you've memorized pi, haven't you? What's pi? 3.14. Use pi is just actually it's a letter from the Greek alphabet that they set it equal to a number. E is like that. E is not supposed to be used for any other variable. Have you ever noticed that we don't use e's in variables? We use x's and y's and z's and these p's and q's and n's, and we never use e's. Why? Because E isn't a variable in math. E is a number. If you haven't memorized it yet, memorize it now. It's 2.718, and it actually goes on forever. If you want to know exactly what it is, you can look up really cool explanations of how they get E. It's this cool number found in nature, and it's also used in calculus, when you get to calculus, you use E a lot. It's the natural log. So log base E, a lot of times, will have an argument. Remember, this position here is called the base. This position here is called the argument of E. And let's say I said it was E to the fourth. Even if you don't really know what's going on, what do you think the answer is? 4. Because the two bases are the same. The answer is 4. Now let's try to figure out what's going on. So I'm going to say equals x. Do you get I said? Anytime there is no variable in it, remember, E's not a variable. E's 2.18, or 2.718, sorry. If there's no variable, you can say equals x. Then I can do a rewrite. Would you please, right now, do a rewrite on this, and I think it'll make sense to you that the answer must be 4. Just rewrite it. This rewrite thing is so critical, and yet I think there's about 1 out of every 7 people in here that don't know how to do it yet, judging by the answers I've been seeing on iPads. So what I want you to do is rewrite this thing and then show the person I'm assigning you right now. And if they don't understand it, would you please show them? Okay, I'm going to pause for a second while I assign you a person. Here's what you were looking for. E to the x. And then you come back over here, and all of this, E to the fourth. And if it's E to the x equals E to the fourth, then obviously x must be the same as 4. X must equal 4. If it's not obvious to you, you got to understand if the bases are the same, then the exponents have to be the same. X must equal 4. Okay, let's actually do some off of your sheet now. So everybody, go find logs day 1. I'm going to pause for a second while I do that. Okay, so the first one should be an easy peasy. Remember, on number 1, I said if there's no x, you could just say equals x and then do a rewrite. I really think this is the best way to go instead of memorizing patterns, because when we get to more advanced logs, you are going to have to understand how to rewrite logs as exponentials. So just say equals x, and then you can rewrite it. 4 to the x equals, come back here, 4. And if the bases are the same, the x must be the same. But you say this has no exponent, then that means there's really a 1 there. So x must equal 1. Could you have got that by knowing that the bases were the same, and therefore it's the exponent on this 4? That's another way you could have got it. Yep. X equals 1. All right, let's move on to number 2. Log base 6 of 1. I'm not seeing this right away, so I'm going to do a rewrite. Equals x. Now rewrite it, and I think, if you think about it, the answer will become clear. Do the rewrite first. You can't just stare at it. That doesn't help. Rewrite it. Mr. P, tell me what you rewrote. Six to the x equals 1. Perfect. Now that might even also not just come to your head immediately, but think about it. 6, what could you put it to? To what power would make it equal 1? X must equal 0. 6 to the 0 equals 1. X equals 0. Anything to the 0 power equals 1. Okay, next one. I'm going to say equals x. Do a rewrite. 2 to the x equals 32. 2 to the what is 32? Yep, that's it. She looked like she was raising her hand, but what was she holding up? What do you think? A 5. 5 fingers. Make sense? X is 5. Because 2 to the 5th is 32. All right, number 4 is easy enough if you understand that 81 is really the same as 3 to the power of... I'm going to make you figure it out. 81 is a whole bunch of 3's multiplied together. You figure it out. And once you know that, and you rewrite 81 as 3 to a power, your answer will become easy. All right, now we got to get into these fraction exponents. We haven't done this in a while. We've done it in this class. We haven't done it in a while. What in the world is happening right there? Well, we can get a clue by looking over at this 6 as a base. Do you get it would be awesome if you could just rewrite this whole thing as 6 to a power? I hope you get that if the problem was like this, log base 6 of 6 to the negative 1/3 power or something weird like that, that this would be the answer. If you get the bases the same, the answer is the exponent. Have you figured that out yet? Do you get that if this is the same as that, my answer is right there? Raise your hand if you get that. Okay, good. Then all we got to do is figure out how to make this mess to be a 6 to a power. Who's got one thing they know about that power? Yes, ma'am. It's got to be a negative power because it's 1 over the answer. Do you remember that negative powers make it 1 over whatever the answer was? Okay, so 6 to the negative. Now, who knows something else about our power? Come on, there's smart people in here. Yes? You think it's the 1/5? I don't think it's the 1/5, but you were thinking that it has a fraction. I will give you that it is a fraction. Something over something. How about this? To get a 6, to have a 36 in the answer, what does it need to involve? Squaring. So 6 has to get squared. Should that be the number on the top or the number on the bottom? Okay, you guys have had too long without fraction exponents, so I'm going to just do a quick reminder. Let's say I had this, 27 to the negative 2/3 power. I'm going to remind you how this works. Remember me saying the roots are always on the bottom? Does that ring a bell? The roots are on the bottom, just like in plants. This is what root it is. This is the normal power. And this means to flip it, also known as the inverse. So this one would be the 3rd root of 27. That's that. 3, because 3 times 3 times 3 makes 27. And then the normal power is 2, so I square it. 3 squared makes 9. And then that last part is, the answer was going to be 9, except it had a negative in front. So then it's flip it. Final answer? 1/9. Okay, man, you guys are really rusty on these. Okay, so I need to take a little bit more time on the fraction exponents. We don't have much time, so pay attention. Okay, so let's say I had this, 81 to the 1/2 power. That's an easy one. Please tell me, remember the 1/2 is the 2nd root, also known as the square root. So what's the answer to this one? 9. What if I make it this? 1 over 9. Does that make sense? Okay, so this would be 1/9. These negative powers make the answer flip. They never make the answer negative. All right, how about another one like that? 25 to the negative 1/2. What would that be? 1/5. Because the 1/2 power is the square root, so square root of 25 is 5, and then the negative makes it 1/5. All right, so back to our problem that we were doing when we got stuck and didn't know how to handle this part. How do I make a 6 into a 1 over the 5th root of 36? Do you see how it says 5th root in there? Please tell me you can see the 5th root. If it's the 5th root, roots go on the bottom. Remember? And then, how do I get the 6 to turn into a 36? Squaring, and therefore there's only one spot left, and it's right there. Do you get how that's 6 to the negative 2/5 power? Now that I've rewritten it as this part right here is now 6 to the negative 2/5 power, since the base of the log and the base of the argument are the same, then the answer is just the negative 2/5. All right. This one here. Do you get we want to rewrite that as a 5 to a power? So this right there needs to be 5 to the something. What would that be? 5 to the what? 5 to the 1/2 would be the square root. You're close. 5 to the what? 1/3 power. There you go. And now that this is the same as that, the answer is just 1/3. Or you could rewrite it, say equals x, and then go, okay, 5 to the x equals 5 to the 1/3. And then that shows you that x must be 1/3. Okay. Now remember, yes? It wasn't, oh, you're right. You're right. It was 25. I just screwed up. It was 25 to the 1/3 power. But if I rewrite this as 25 to the 1/3 power, do you get that the bases aren't the same? So then I got to rewrite my 25 as a 5 squared. So that 25 becomes 5 squared. And now I've got my 5 just like I wanted. I just have to multiply these two, and that's my power. 2 times 1/3 is 2/3. All right, now I know this is not going to be a walk in the park tonight, but I've done a lot of practice problems with you. You should be able to get a bunch of these right. I don't expect you to be perfect. Tomorrow, Mr. Winterhalter comes in and basically gives you a review day on this, and the day 2 worksheet is assigned in class, which is just like today's. Okay? So yes, these are stretched because I tried to teach you a week's worth of log material you learned last year in 1 hour. Okay? So yeah, you might be feeling a little bit on the edge, but tomorrow's a review day. Hopefully by the end of tomorrow you're solid on logs again, and that'll depend on you being able to ask if you're stuck. Mr. Winterhalter has been teaching this stuff for a long time. He knows how to do it. Totally can help you. And the kids next to you oftentimes are good resources too. Don't be afraid to ask them for help. All right. What does this number 8 have? What's doing on number 8 where you have no base? What do I do if there's no base? Remember? Number 8 has no base. Help. What's the base? That's base 10, really. And then if I could rewrite the 10,000 as 10 to a power, then I'd have this beautiful situation of it being, these two numbers being the same, right? So it's 10 to some power, and then that one should become easy. This one already is 10 to a power, so since there's no base, I can put in a base 10, and that one becomes really easy. I think your hardest part is going to be when you have to rewrite something like that as 10 to a power. Because this is log base 10, and that means this guy needs to be written as 10 to the negative, because it's a fraction, because it's flipped. Fraction power, the root part is a square root. And how do I get 10 to turn into 1,000? 10 times 1 is, or 10 to the 1 is 10. 10 to the 2, how about 10 to the 3? I think it's 10 to the 3rd, isn't it? Okay. And what does ln mean? That's log base e. So everybody on number 14, please rewrite the problem as log base e of e to the negative 4. If you can learn, anytime you see ln, it means log base e. Then those problems become really simple. So this one becomes log base e of 1. And if I told you if there's no variable, remember e's not a variable, I can say equals x, then you can do a rewrite. And you'll go, okay, so e to the x has to equal 1. So how do I get 2.718 to a power to equal 1? Oh yeah, 2.718 to the something is 1. You got to figure that one out. All right, that was a lot to relearn in one day, but I tried to teach you so much so that tomorrow would be much easier. Tomorrow you can just hopefully review what you learned today. All right, the rest of your time today, which there's not, it's like 10 minutes left or so, is finishing up this worksheet. I don't want you to skip any of them, even though there's a bunch. I did a bunch with you already, or for you, I guess you could say. So I don't want to cut this thing down. Remember, if there's no base, you got to give it a base. Seems like there's no base here, but you can rewrite ln as log base e. Then it'll have a base. Log base e of e to the 12. And then once they got this little pattern going on, they're easy. All right, this one's going to freak some people out. I'm just going to say equals x. Remember how I said if there's no variable, you can say equals x? Then try to rewrite it as a log. And this has a base 10, log base 10. You can try to rewrite that one as a log. That one's definitely your stretcher question. It can be done. If you're one of my top kids, prove it. Figure that one out. Okay, that's all I have for you for today.